The relationship between a taxpayer and the state ends at the exact moment of payment. You hand over a specific, quantified portion of your labor, and it immediately vanishes into an undifferentiated pool of sovereign revenue. Once the money enters the Treasury, your visibility into its final destination is severed. Current fiscal tracking systems operate entirely in retrospect and in aggregate. You can see how many billions went to a specific ministry, but you cannot verify which specific school, contract, or agency your individual contribution funded. The Citizen Fiscal Objection, or OCF, is a proposed constitutional framework designed to close this informational gap. It grants taxpayers a legally protected right to trace their specific financial contributions and register formal objections against budget allocations they view as corrupt or illegitimate. This is a narrowly framed negative veto. Citizens cannot dictate where their money goes. They only retain the right to specify where their individual tax units must not go, leaving the state's total revenue and legislative authority completely intact. To enforce a per-citizen veto without fragmenting the national budget, the state must be able to prove exactly which taxpayer funded which account. The strict technical prerequisite for this framework is achieving individual tax traceability at a national scale. Historically, governments rely on the retrospective aggregate audit, reviewing broad spending categories long after the money is gone. The OCF replaces this with ex-ante granular attribution. It builds a precise map of who is funding what before a single dollar is actually disbursed. Audit courts act too late to recover stolen funds. Deterring systemic fiscal abuse requires informational visibility at the exact moment of expenditure. This framework treats individual tax tracking not as a macroeconomic ideal, but as a baseline requirement for institutional hygiene. When engineers are asked to build a tax traceability system, their first reflex is to track a digital dollar chronologically. They attempt to follow the money from the citizen's bank account through the central tax authority, across various Treasury intermediaries, and into a final public contract. That approach fails immediately in production. Attempting to map millions of individual taxpayer inputs to thousands of dispersed government outputs creates a combinatorial explosion. This is a classic graph traversal problem. As the number of intermediaries grows, the computational cost scales quadratically. Running that chronological tracking math in real time for a nation of 50 million citizens is computationally impossible. The OCF architecture solves this by abandoning chronological tracking entirely. Instead, it operates as an ex-ante pre-authorization matching system. The system assigns a taxpayer to a button account mathematically, bypassing the physical flow of funds through state accounts. We are going to examine exactly how this architecture works. It relies on an algorithmic technique called positional decomposition to break down contributions, and utilizes local hash chaining instead of distributed blockchain ledgers to secure the data. By structuring the pipeline this way, empirical modeling proves a sovereign state can achieve permanent individual-level tax traceability for exactly 0.0001 cents per transaction. Transforming national fiscal transparency does not require infinite compute power. It requires a specific shift in logic, replacing the impossible task of tracking money backward with the highly efficient math of matching it forward. The primary bottleneck in traceability is data volume. If you track every single cent a citizen pays, the database collapses. The OCF system prevents this using positional decomposition, a method that fragments a tax contribution into a highly restricted number of standardized traceable units. This diagram shows a hypothetical taxpayer's net monthly contribution of $15,708.32. The algorithm decomposes this amount by extracting its non-zero positional digits. First, it isolates the value at the 10,000s position, generating a single traceable unit worth exactly $10,000. Next, it extracts the digit at the thousands position, yielding a $5,000 unit. It repeats this for the remaining integer digits, pulling out a $700 unit, skipping the zero, and extracting an $8 unit. Finally, any remaining decimal value below the system's minimum threshold is consolidated into a single residual unit of 32 cents. This structural decomposition guarantees deterministic conservation. Every cent is accounted for across these 5 units, producing 0 rounding errors for the public audit. A chart showing contribution magnitude on the x-axis against the number of generated units on the y-axis. Because the algorithm follows base 10 logic, the fragment count grows logarithmically. even as payments scale into billions, it produces a maximum of 7 to 9 individual units. For a national economy with 20 million active contributors, the math is entirely predictable. The system will generate a hard cap of roughly 87 million traceable units per monthly cycle. By anchoring the data generation to positional logic, the OCF bounds its own database workload natively. It takes an infinitely complex tracking problem and compresses it into a finite, highly manageable dataset. Once generated, all citizen traceables are loaded into a denomination matrix. This is built on an in-memory database, specifically DragonflyDB, a high-performance data store that indexes data entirely in RAM for rapid retrieval, organizing the millions of units strictly by their dollar value. Before any money is matched, the state's budget accounts are queued. They are sorted in ascending order based on their objection index, or IOF. The IOF is a metric calculating the ratio of active citizen objections against a specific account relative to the population size. Thus, the least objected accounts get funded first. When an account reaches the front of the queue, its required transfer value is decomposed using the exact same positional math, creating a demand vector of specific denominations it needs to fill its balance. This animated diagram shows the system executing an spop command, a set-pop database operation that removes and returns a random element. The account requests a $5,000 unit, and the matrix randomly ejects one matching traceable from the citizen pool. This is where the architecture handles citizen vetoes. The system does not cross-reference every citizen's objection against every budget account in advance. It only performs an objection check on the specific traceable after it is randomly drawn. If the contributor who generated that unit has registered an active objection against this specific budget account, the unit is rejected. It drops back into the pool, and the system instantly draws a replacement unit, verifying it against the new citizen's record. Processing accounts sequentially by their objection index creates a deliberate structural consequence. Highly objected accounts are processed last. They are forced to draw from a depleted, fragmented pool, requiring a massive number of individual citizens to piece together their funding. Those citizens then see that account on their personal transparency reports. Thus, the architecture crowdsources the audit natively. Evaluating objections per draw rather than pre-computing a massive matrix makes granular citizen vetoes computationally trivial. The modern tech industry reflex is to assume that any tamper-evident public record requires a blockchain. The initial assumption for OCF was that this allocation logic had to run on an Ethereum Layer 2 or similar distributed network. That reflex suffers from a consensus mismatch. Blockchains are engineered to establish truth among mutually distrustful parties without essential authority. In a sovereign tax system, the state is already the central custodial authority. This table displays the financial penalty of that architectural redundancy. Even using optimistic Layer 2 gas prices, routing 174 million monthly operations through a smart contract costs $1.7 million a month. That is 192 times more expensive than running the identical logic on fixed infrastructure. To protect the allocation logic without a blockchain, the OCF relies on trusted execution environments. A TEE is a secure, hardware-isolated area of a processor that executes code in a quarantine state, inaccessible even to the system administrators. The TEE provides computational opacity. No one can see the raw citizen data inside, but the hardware generates cryptographic attestation proofs, verifying that the open-source code executed exactly as written. To guarantee the final records are immutable, the system uses isolated batch hash chaining. At the end of the night, the processing log is sealed using SHA-256, a cryptographic function that generates a fixed, unique signature for that specific dataset. That signature is permanently locked into the header of the next day's batch. If a corrupt official attempts to retroactively alter a taxpayer's allocation in a previous batch, the math breaks. The hash mismatch ripples through every subsequent day, making the tampering immediately detectable by any independent auditor, without requiring network consensus. By combining open-source code, hardware enclaves, and simple hash chains, the system achieves the exact same cryptographic tamper evidence as a public blockchain, but executes at a fraction of a cent per transaction. The architecture is complete. A citizen's payment is positionally decomposed, indexed in memory, matched to accounts via just-in-time objection checks inside a hardware enclave, and permanently sealed in a hash chain. This dashboard visualization shows the results of a stochastic simulation modeled on the official Colombian tax base. Processing nearly 1 million citizens for a single daily batch generated roughly 4 million traceables, and it completed the entire matching pipeline in under 30 seconds on consumer-grade hardware. The workload easily fits within a standard nocturnal administrative window. When modeled for a nation of 50 million citizens and 20 million active contributors, the annual operating expense to run this dedicated infrastructure and its oversight personnel sits at $2.3 million. That operating expense represents exactly 0.002% of the total national budget. It is a fraction of the cost required to run traditional, retrospective state auditing bodies. The return on investment is immediate. If the deterrent effect of 20 million citizens actively observing specific budget accounts prevents even a fraction of a percent of estimated annual corruption and inefficiency, the system covers its own costs. Under a realistic conservative model, the entire infrastructure investment achieves payback in under 3 weeks. Individual tax traceability is a fully solvable data architecture problem. We have the hardware, the math, and the code base to implement continuous, granular fiscal accountability. Turning the black box of government spending into a transparent, accountable ledger is now merely a political choice.